when the robot follows this gradient descent, it will go by the most safe path in the environment. And this is something that there are many approaches with potential fields, and here in Porto Alegre is one of the most important works. The works of Edson Prestes were in this area. And finally, another approach is the sampling-based approach, is a probabilistic approach. In this case, we do not need to compute the whole configuration space, so we want to avoid the explicit construction of the space, and instead conduct a sampling scheme. The idea is to, given the space, we sample endpoints and build a graph over this environment using all these points. And with this graph, we can compute trajectories that guide the robot to the goal. And the idea is that if we use enough points, lots and lots of points, the solution that we find will become closer and closer to the optimal solution. So if we have time, we can generate lots and lots of points. But if we do not have, we can generate a few points and find a roadmap that maybe is not that good, but it was generated fast. Okay, and so here are examples. Now, as I saw there, let me see here. We passed the 45 minutes, right?
Yeah, we're up to the break. Yeah. So it's
yes.
3 o'clock now, and so maybe we'll just take a break for 10-12 minutes and come back at 3:15 for the continuation. Yeah, thanks for the great lecture so far, Renan. Yeah.
Okay. So let me continue here. The last problem that I want to talk is let me see, the localization problem. This is the hardest of the 3 problems that I'm presenting. Basically, we want to know where the robot is. So we do not know the robot position, and we need to determine this position based on the observations made by the robot and comparing these observations with the map that we have. Localization approaches are usually probabilistic approaches. So we use filters such as Kalman filters, particle filters. The input for the problem is the map and the actions made by the robot and the observations. We want to estimate the robot trajectory. Okay. There are variations of this problem, and one of this problem, one type, is the local localization problem, also known as position tracking. So in this type of problem, the initial robot pose is known. So we know where the robot started moving, but then when the robot moves, we need to estimate the correct position of the robot. And why this is necessary? Because the actions of the robot are not quite precise. So if you tell the robot to move 1 meter, the robot will move something near 1 meter, but maybe less or more. And there is an uncertainty in this motion. And after some time, this uncertainty grows, and then we do not know what the robot is. In this type of problem, position tracking, the pose uncertainty is often approximated by a Gaussian, a unimodal distribution. So we know we have an estimate of where the robot is, which is the mean of this Gaussian, and we have an uncertainty of the robot position. This is the easiest problem of localization. There is another type of problem called global localization. Here the initial pose of the robot is unknown. Okay, we only turn on the robot and start to move in an environment, and we need to know where the robot is. In this case, we cannot use unimodal probability distribution, such as a Gaussian. We need to use something different. And in global localization, only after some time we'll be able to localize the robot, and perhaps, depending of the motion of the robot, we even maybe not localize correctly. The global localization includes the position tracking problem. So after some time, when we solve the global localization, we still need to perform localization, but in this case, position tracking. To talk about the global localization problem, I need to talk about the base filter, because all the approaches for localization are based on the base filter, and base filter is a probabilistic tool used for recursive state estimation. So here we will use the Markov assumption that I talked earlier to estimate the state of the system. The state here is x, is the position of the robot, and this bell is the belief of the position. And using base filter, we model this belief as a distribution of xt given all the observations from time 1 to time t minus 1 and all actions made by the robot. And the base filter is divided in two steps, a prediction step and a correction step. So in prediction, we update the belief of the state. So we predict this belief based on the motion made by the robot. And in the correction step, we update the belief based on the observation. So if you look at the equations here, the only difference in the distribution is that in the correction, we are considering also zt. So we are considering z from time 1 to t. So zt is the current observation made by the robot. While in prediction, we consider only the observations from z1 to zt minus 1. Okay. I will present what we do in how the base filter works. The idea is that, well, we want to compute this belief of the state. This belief is a distribution of a probabilistic distribution based on observations and actions. But we do not know this distribution. So the base filter applies the base rule over this probability. And the base rule is used when we want to represent a probability, for instance, the probability of A given another variable, b, and possibly other variables, c. In this case, there are lots of variables in our distribution, but basically, we want the probability of A, but we do not have this probability, but we have the probability of B given A, and we have the probabilities of A, probabilities of B. Okay, so we do not have this probability of xt given z and u, but we have the probability of zt given xt and all the other variables, and the probability of xt given the previous observations. So here is the probability of xt given z1 to t minus 1. U from 1 to t we will not consider, so we'll let in the right side of the probability here, such as c in the example of the base group. And this eta is a normalization constant here, and it's something that will not impact in our computation. But then we need to optimize this equation, and now we use the Markov assumption. The Markov assumption says that the current state depends only on the previous state and the action, the current action. And the Markov assumption also says that the current observation, what the robot observes, depends only on the current state. So the zt depends only on xt. It does not depend on z1 to t minus 1 or the actions. Because if we know the current state, we can estimate the observations. So this is a simplification that we need to perform. The other term, p of xt given z1 to t minus 1 and the actions, all the actions, is the belief before correction that I said earlier. Okay. Is the belief that we have considering only the current action, but not the current observation. So now the belief xt is given using this probability, zt given xt, that, as I'll show later, is the observation model, and this belief. But this belief we do not know. So we use another law, the law of total probability, and the idea of the law of total probability is to compute the belief in time xt based on the belief in the previous time. So we perform the integration of all the transformation from time t minus 1 to t from all possible x t minus 1. So we apply this law of total probability, and we have this integration. Again, we apply the Markov assumption. So with the Markov assumption, we said the current state only depends on the previous one and the current action. So it is what we have here. And this other term here, we also apply the Markov assumption because the belief in time t minus 1 does not depend on the action in time t, because it will occur later. So we eliminate this variable. And this term, p of x t minus 1, z from 1 to t minus 1, and u from 1 to t minus 1, is the belief in the previous state. So what we do in the base filter is to build a recursive term. So with the base filter we have, in prediction, we update the previous belief using this probability of xt given xt minus 1 ut, which is the motion model. So we apply the motion in the previous state to update the probability. This is a prediction. And then we perform a correction we apply an observation model over this predicted belief to correct it. Okay. So in practice, how works the localization? We need to start with an initial distribution. Okay. The initial belief about robot location in the global localization problem. Initially, the robot can be anywhere, so we do not know where the robot is. So the belief is a uniform distribution. In this example, the robot can move to the left or to the right, and it can observe a door or no door. Okay, it's a simple example. Then, applying the base filter, what the localization does is, the first observation is door. Okay. Then we can correct our belief using this information. We are able to adjust the belief. So, if we know the map of the environment and we know there are 3 doors, we can correct this uniform distribution with some observation model. And the observation here is a Gaussian applied in each door of the environment. So the robot can be in front of any of the 3 doors. This is just a correction of the distribution. If the robot moves, we need to perform a prediction. So we apply the motion model in the distribution. For instance, the robot moved 1 meter, we perform a shift in the distribution of 1 meter. Okay. An important point is that the distribution must be smoothed. Because the motion is not that certain, so we also apply a Gaussian in the shift, and we can see that the peaks of the distribution are shorter now. The distribution is more spread in the state space. So after prediction, the robot performs a correction, then it will perform a prediction, correction, and keep doing this. So when it performs a correction is based on observation. The robot observes a door, it corrects the distribution. So it applies again the observation model. In red is the observation model. Apply it over the previous state, and it corrects the state, the distribution. Okay. After this observation, the localization algorithm places the probability mass near the second door. So after basically 2 steps, we already know what the robot is, and this is what is done in localization. So here the robot moves right once again, and after some time, the distribution becomes a unimodal distribution, like a Gaussian. Okay, so the core of localization strategy is basically sense and act, where after we start with an initial belief, then we perform an observation. This observation decreases the uncertainty in the application of a correction. So when we observe something, we improve our estimate. After some motion, we perform a prediction. We perform a prediction, and this prediction increases the uncertainty because motions are uncertain. Observations are much more certain. So the localization is a cycle of prediction and correction. And later, when we show tomorrow, when I talk about SLAM, the techniques of SLAM use this. Most of the techniques use this this approach of prediction correction. Okay, and one of the most popular approaches for localization is particle filters. And because particle filters can deal with arbitrary distributions, the idea is to spread particles in the environment, use multiple particles to represent a distribution. The more particles fall into a region, the higher the probability of the region. So this is also called Monte Carlo localization. And the idea is I'll present it in an example. Initially, you spread particles in all the environment. Then we perform an observation. In this case, the observation is measurements of a laser rangefinder. And with an observation, we must compute the observation model. The observation model in a particle filter is responsible for weighting the particles, for giving a weight to the particles. So particles where the observation of that particle matches with the observation made by the robot will receive higher weights than particles where the match is not good. And in particle filter, when after performing an observation, you perform the resampling. The resampling is that we keep particles with good weights, particles that as we weighted, they are more similar to the current distribution observed by the robot. And we eliminate particles with bad weights. Okay. Then, after the resampling, the robot moves, we perform a motion update. So we apply a motion in all particles. These particles move in the environment. And then we perform measurements, update of the weights, resampling, motion, and you keep doing this cycle of operation until all the particles try to tend to concentrate in a region. So this is an example of localization. Okay, and so those are the three basic problems: mapping, localization, and motion planning. The composition of these three problems generate different and more advanced problems, such as SLAM, which is simultaneous localization mapping, exploration, which is motion planning applied to mapping, active localization, which is motion planning applied to localization, and the combination of all problems that we call integrated exploration. Of those problems, SLAM is the hardest one. Simultaneous localization mapping is the hardest one because it is called a chicken or egg problem. Mapping, as I showed earlier, the mapping depends on a good estimate of the robot pose, and localization depends on the map. In SLAM, we do not have any of those two things, and we must estimate both at the same time. So this is the hardest problem. The other two, exploration, is basically find the best motion strategies with mapping. So we use mapping to help, we use motion planning to help the mapping. In active localization is find the best motion strategy to solve localization. So once again, we use the planning to improve localization. And SLAM is different. SLAM depends on both. And the integrated exploration, also called active SLAM, usually what we do is to find the best motion strategy to solve SLAM in this case. So all these three problems, exploration, active localization, and active SLAM, they can use, for instance, in integrated exploration, they can consider SLAM as a black box, and we focus on what are the best motion that improves SLAM. Okay. So it is for this reason that I say that SLAM is the hardest. But this is something that I'll talk in the next lecture. Islam and integrated exploration. Okay. Let me go back. And that's it about the lecture of today. Thank you for Charles and everyone. Any questions?
Just so if anyone has a question that they want to put in the Slido, now's the time. I'm not seeing any. Did anyone? Does anyone have a question they want to just yell out? Maybe you could give us a preview of what we're going to hear tomorrow.
Okay.
Renan, just a verbal.
Tomorrow I'll focus, so there we go, in Islam. And Islam is the main problem of mobile robotics in the last 20 years and or more. And because in practice this is what we have. We do not have let me show here. In practice, we do not have a proper estimate of the pose of the robot. Usually the map is not fully known. We maybe know some parts of the map, but not all, or not with a great precision. And so, to let the robot move in an unknown environment, move in the streets, we need to perform SLAM. And starting in the 90s, when the first solution of SLAM was proposed, many researchers have been focused on this type of problem, and today the focus is basically on solving Islam using cameras in outdoor environments, focusing on autonomous vehicles, right? So tomorrow I'll spend some time explaining Islam. I will show two approaches of Islam. The first one is this, a Kalman-based approach, which is it's a simple implementation of the base filter for Islam. And then I'll talk about the graph-based Islam, which is the state-of-the-art of Islam. And I'll enter in details tomorrow, but I'll talk about what are the main problems here that we have. And another problem that I'll talk is the integrated exploration, which is an important way of improving Islam, is trying to perform movements, motion that are good for Islam, because Islam depends on a series of characteristics in the environment. It depends that the robot is able to collect features and distinguish these features in the environment. And depending on the navigation, if the robot goes to regions that there are no features, the Islam will fail. So integrated exploration is an important topic. I'll talk also. So I'll talk about one technique of integrated exploration tomorrow. Okay?
Yeah. Cool. All right, everyone, maybe we can just thank our speaker for the day.